Okie dokie. Hello everyone, and welcome to DAV Workshop 3 on Designing Fancy Graphics. So first of all, we're just going to get right into it. Most of you have done Lab 5 by now, a few of you have not. But if you have looked at Lab 5, in the extra credit section, we introduce a topic known as blocking. So we're going to quickly run through what blocking actually is. So as we've discussed before in lecture 5 particularly, we use ping-pong RAM to store all of the pixels that go onto the display. And using ping-pong RAM, using this double buffering method, allows us to eliminate screen tearing. So with a 640 by 480 VGA display, that's going to be a very large number of pixels, specifically 614,000 bytes for 2 buffers. That is a lot of memory, and typically we use the on-chip memory on the FPGA, so the on-chip memory on the FPGA is not going to be enough to store all of this. So we have a couple solutions to this problem. We can use larger arrays of memory that are located off the FPGA. This is like off-chip memory, also known as block RAM, also known as SDRAM. You might have seen it in the IP catalog. It's just a thing that exists on our FPGAs. This has been experimented with in the past with limited success. We had more success this year, but the success came after we made this workshop. So it's not covered in this workshop. Anyway, you could do that, or you could use display blocking, which is the graphic sensation that's sweeping the nation. Anyway, so with display blocking, basically what we do is we consolidate squares or rectangles or other regions of pixels into larger blocks. Each group of pixels will always have the same color, and so you can represent the color of multiple pixels on your display with just one actual pixel color, like one byte. So this significantly reduces the number of pixels in memory. Like as you can see here, this is a system where you have blocks of 20 by 20. The original display requires 614 kilobytes of memory to store all the pixels. You get a slightly reduced resolution if you do it this way, but now you're only dealing with a 32 by 24 pixel display, and that gets like basically your memory is almost zero. Justin.
Is it feasible to like dynamically increase the resolution if you use
I mean, it can be if you like try hard enough, but it kind of defeats the purpose. And because the main reason we do this is to reduce the usage of FPGA resources, namely because like the logic elements are what we use to convert to on-chip memory. So if you're increasing the complexity of your system by creating like a dynamic blocking system, well, for one, keep in mind that your logic element usage can only be as low as the like highest resolution blocked display that you intend to render, and you're also going to have the overhead of actually generating this like dynamic blocking system, and you have to allocate like memory for the entire thing and then use parts of it. It's just kind of a pain. So I would not recommend this, but if you think there's some sort of benefit to it, I would love to hear it, because obviously I'm not an expert on this. Sparsh.
Could you have like different size blocks in different parts of the image? Like if you know that
Oh,
that top part
absolutely.
will always be like one color, just like have a giant block.
Yes, you can.
Okay.
So that's another thing we'll actually talk about later, but you can actually have different windows in your display, each of which have like independent resolutions, and you can compose them. So to implement blocking, it's actually fairly simple. We'll just go over some quick terminology. What we're going to do is we're going to define a scaling factor, a scale x, and a scale y, and this will determine how many pixels make up each block. So as I showed earlier, our scaling factor was 20 for both dimensions, which means that, hello, come in, which means that the display resolution was 32 by 24, and each pixel of the 32 by 24 display was actually 20 pixels, like in the actual hardware. Like, as I said here, if you want to have like differently sized blocks, or like blocks that are rectangles, you will have to define 2 scaling factors, otherwise you can get away with just 1. So in our VGA module, as part of the implementation of it, you define a horizontal and vertical counter. So in order to actually implement the blocking, what you're going to do is you can calculate the graphical coordinates by dividing your horizontal and vertical counter, which are some number between 0 and 640 or 0 by 480. You take that number, divide it by your scaling factor, it's like 20, and that gets you your coordinates for the blocked region. It's fairly straightforward. You can define the origin wherever you like, depending on what sort of graphical system makes the most sense for your capstone. And we typically just use the top left for when we were making Tetris. So you are sacrificing resolution, of course, but most of your capstones will probably use some variety of pixelated graphics. If you aren't, you may need to look into the SDRAM. We have code that works for that, so if that's something you feel like you need, you should message us after. Also, one more thing, for any of you doing the digital audio visualizer capstone, you can note that you can probably reduce the resolution of your display significantly if your blocks, quote unquote, are just like 1 pixel tall and the width is just the width of an FFT bin. Because in theory, you're not going to change the actual, you're not going to change the pixel color within the same bin, unless you plan on doing some sort of fancy coloring it to that extent. But if otherwise, that's a fairly straightforward method of reducing the resolution and memory usage of your display. All right. And now that we've gone over blocking and pixelated graphics, we're going to talk about sprites. So for a lot of your capstones, you will have basically small, reusable graphical elements. These are basically what sprites are. So any sort of graphical element that's a little bit more complex and you can reuse in multiple places, or otherwise control sort of all in one piece, that's going to be a sprite. So some examples are this drawing of Mario or the Tetris pieces up in the corner. When your graphics are simple enough, you can actually just like hard code your sprite directly into a graphics module. You can write like a combinational module that takes in an input coordinate and takes in like a sprite and just outputs a given color in that particular sprite. That's kind of weird and like it'll get really messy really quickly. So what you should do instead is you should store this sprite in memory somewhere. Additionally, for the same thing goes for if you take a sprite that you made and you want to be able to easily change the colors. Like say we had the picture of Mario earlier and you want to give it the Sedant fit with the blue hat and the IEEE polo. So if you want to do that, you have to change your graphical module in many places because all of the colors will be different in various places. So even though the regions of similar colors are going to be the same, the actual colors will be different, so you need to make changes to your module. And that kind of sucks. So sprites help us make the graphics a little bit more modular by making the actual pixel sort of, all of your pixels are a little bit more unified. You can control them all in one go, and therefore it's just a lot easier and more reusable. So in order to do all of this, we've established that you're not going to be using a combinational module to generate sprites. So what you should do is you should store them in memory somehow. What we recommend is some sort, either a lookup table, like a very large register basically, or some sort of ROM, read-only memory. There are benefits to each one. If you're using a lookup table, obviously your lookups are going to be very fast because lookup tables are just registers that you can immediately read from in your module. Implementation is going to be very easy, and however, you will be limited by FPGA space constraints. You will only have so many lookup tables that you can generate in your FPGA. However, if you're using ROM, you can it'll be a little bit slower because it takes a clock cycle to access, and the implementation is slightly more annoying. But there are IPs, and also you get a lot more space this way because they tend to be space optimized. If you want extra fancy features like animated sprites, for example, which we'll briefly talk about, we recommend you store your animations, all the different versions of your sprite. You store them in ROM somewhere, and then you load in the next animation cycle into a lookup table for every frame, every time it changes. And this is a good way to implement walk cycles or other sorts of sort of steady animations in your system. They can also be unsteady if you want. That'll be a little more complicated. So regardless of whether you use a lookup table or you use ROM, the general structure is going to be somewhat similar. You'll have a bunch of parameters that indicate where you're in your memory. It's going to be a start address for your sprite and the length of your sprite in bytes. And what you'll do is you will hard code these into your module somewhere because these are just memory addresses. And then in the lookup table, you will store the color of each pixel as a singular byte at each byte in your ROM or lookup table, which is typically byte addressable. And you will use these parameters to access the bytes out of that spot. You might not necessarily need this much complexity. So if a lot of you might be implementing a system with sprites that are just all one color. if this is the case, you can actually avoid doing this entirely because you can just store the sprite as a bit field of pixels, and then instead of storing the color, like you just hard code the color somewhere because it's just like one constant color. And this will significantly reduce the number of bits you use to represent a sprite, because if it's all one color, you don't have to store each color. So as you can see here for Tetris, this is an example of what we did. You take like the Z piece, for example, which kind of goes like this. We just stored a bit field of where 1 represents the pixel being like existing in a certain spot, and 0 just meant there's no, like, there's this part, the sprite is not there in that pixel. And we have the same with the T piece and stuff. So if you're using ROM for things like animation cycles, you'll probably have a lot of different, you'll have the same sprite in, like, slightly different in a lot of places in your ROM. So in various, like, after every frame, you're going to want to load in from your ROM each byte of your sprite, your next animation cycle, into your lookup table. Does all of that make sense? Okay. So quickly to summarize, the bottom line here is you're going to use lookup tables anytime you're like actively using a sprite. You need to be able to render its pixels on the display, like in that frame. And if needed, if you're using animations and stuff like that, you can update that lookup table with other sprites from a secondary like ROM that you can contain additional sprites in. This is also a good way to optimize your memory usage by, for example, using by keeping sprites that aren't used very often in your system off the FPGA. All right. Next, we're going to talk about the graphics controller. So we need to link up the VGA driver, the graphics controller, and the frame buffer in a way that the frames are always ready for the VGA driver at the appropriate time. This is something we talked about in all of your design reviews, but we will quickly go over it again. So we discussed the general like block diagram. What we're going to do is kind of go a little bit more in detail. There's two ways to do this. Hello. So the easy way will guarantee synchronization with your ping-pong RAM and your display, and it'll work for most cases. The hard way is more common in the real world when games are more complex and require more time to render the logic. So the easy way to do this is to go pixel by pixel and update at every given edge of your VGA clock, your 25 megahertz input VGA clock. You're going to update the ping-pong RAM with a pixel that's generated by a graphics controller, and you're also going to update your VGA display with a pixel that is read from your ping-pong RAM. Your graphics controller and your VGA display will stay perfectly in sync, always reading from and writing to your ping-pong RAM at the same spot every single time. So there's a few downsides of this approach. The main one being that this doesn't really reduce screen tearing unless you specifically make sure that things cannot change outside of your 60 Hz clock. Your 60 Hz clock being the display refresh rate. And you would have to, as a result, make your game controller operate at a 60 Hz clock. This can have limitations on the complexity of your game logic, because obviously if the clock is not variable, it's a little rough. But the major upside of this is that you don't have to worry about a lot of more annoying things that you would have to if you are updating the ping-pong RAM buffers not in the synchronized manner. Sparsh.
So what would happen if for the game the user were to enter two commands that are faster than the time it takes to go from one ping-pong RAM to the other?
What do you mean, commands?
If you're I don't know, you tell a sprite to move left and then right, but you've done that while it's still writing to one of the screens.
Well, assuming you use this method, if your game controller is forced to operate at a 60 Hz clock, then the only control that will be read is whatever control is currently being input at the clock edge.
Oh, I see. Okay.
That's a good question. Any other questions? Okie dokie. Yeah, so there's a harder way that some people have attempted. I think, Brian, you attempted this, where basically your VGA driver is going to read as normal, pixel by pixel, from your ping-pong RAM module. However, the graphics controller is only going to write to a handful of RAM addresses for pixels that have changed in your game state. So the upside of this is that your game controller can operate however fast it wants, and all it has to do is basically enqueue a bunch of changes to various pixels on your display. A good way of calculating this is, say, you keep track of which sprites are moving or changing in some way on your display. You keep track of their bounding boxes, and then the pixels that you queue up to be written to in your ping-pong RAM are just going to be the pixels that are like contained within the bounding box of your sprite's previous location and its new location. And if you can find an optimized way to do that, then you will be able to basically reduce the number of writes you do because you're not writing every single pixel every time. The downside, of course, is that that's very complicated, and if your game is like doing a lot of intensive computations, and it's gonna help, but we're not gonna bother with that. Real graphics cards do that. And if you are using like G-Sync, for example, this is kind of what enables that sort of behavior. Are there any questions about the fancier way? I encourage you guys to try implementing it if you have nothing better to do. All right, now we will move on to windowing. This section isn't going to be very detailed. It's just going to be sort of like an introduction to what this is to get you guys to understand the options you have available for making more complex games. So windowing allows you to split up your screen to display multiple things at once. If you want to display, for example, let's say you're, I don't know, making a game and an FFT, and you want to display the FFT histogram in one side of the screen and the game in the other. It's like Subway Surfers on the bottom for to retain your viewer's attention span. You could do that with the windowing, where basically you have two graphics controllers, each one controlling a smaller region of the display, say like 320 by 320, or 320 by 480. And then as a result, your graphics controllers are now generating two independent windows of content that you can then put on your display by composing them together. So imagine that your VGA is divided up into 4 windows, and you have sort of these random images that you see here. When the graphics controller is going pixel by pixel, you'll need to keep track of the sort of bounding box of each window, and it'll basically check within each bounding box to determine which window's pixel it should be pulling out. So to do this, you would implement separate graphics controllers, one for each window, and you'd use some sort of multiplexer logic. That should be fairly straightforward, it's just if statements in Verilog. So if you have windowing on top of each other, then if the layers are opaque, like the background of each window is opaque and you can't see through it, that is fundamentally the same thing. You're just going to have to pay careful attention to what order your if statements go in, because obviously you want your windows that are on top to display their pixel and not the ones behind them. If you're windowing with transparent layers, you're going to have a little bit more trouble because you need to somehow take the pixel color of the top layer and the pixel color of the bottom layer and generate a new pixel color based on that. If we approach frame buffering the easy way described before, where we just go pixel by pixel and synchronize everything, you have to generate these stacked pixels combinationally because you will not meet timing constraints if you try to do it on a clock. You have, for example, you have a 25 megahertz clock controlling your graphics controller output, and you have to somehow compose an arbitrary number of pixels sequentially. So on some clock edge, and if our FPGA is a 50 megahertz clock, you only have two clock cycles in which you can compute that stacking, so that's at most 2 layers. Therefore, you will have to limit your stacking of pixels to some limitation and then use combinational logic to generate the composition of them if you want to do transparent windowing. However, if you want more windows, or say like more complex shapes for your windows, then you will have to do it sequentially because the logic will be too complicated to do it just like as one giant combinational module. We haven't tried to implement this ourselves, but we know it can be done. And color composition itself is not too bad. It's just a matter of how you're going to do it sequentially. But yeah. On that note, oh, sorry, I saw a question.
Is there a formula for color composition, or is it just like something we customize every? Oh.
Further questions?
Yeah.
All right. So, now we will talk about color composition and the formula for color composition. So, if you have a color layer that's transparent and on top of another color layer, you're not only going to see the top layer, but you're also going to see some effect of the colors below. So in this case, we have red with green behind it, and as you can see, red is on the top because the resulting thing is orange, which is mostly red. You mostly see what's on the top, but then you also see the sort of lighter shade of green that's causing the red to become much lighter in the background. The result is actually a single opaque shade that we can get by mathematically combining red and green in some fashion. The formula is actually very simple. So if you assume these are our two colors, you have the first color, which is all red, 25500, and a 50% opacity. And your second color is green, so 0, 255, 0 RGB, and a 50% opacity. We're now going to basically do this with vectors, because we can. So if you define your colors as vectors in this manner, you have a color set this and that, and this is our background. This is the shade of blue that's on this slide. This is the opacity of the background, because obviously if the background were not opaque, you would be able to see the whatever's behind. So this is the formula for color composition. You don't need to try and make sense of this yourself. I will explain what it's doing. Basically, what we're doing is we are multiplying each color by its opacity, and then say you have the top layer with a 50% opacity. That leaves 50% of, that's basically saying that the top layer contributes to 50% of the shade of the final color. So 50% of the shade of the final color is just going to be all red. The rest of it is going to be split between all the colors behind red. So in this case, we have green with 50% opacity, and then the background of blue. So if green is also 50% opaque, it contributes 50% to the remaining region of the color, if that makes sense, like the remaining proportion that hasn't been already occupied by red. And then, since our background is 100% opaque, it's just going to take up the rest of the space. As you can see, eventually, when you're doing this, you're always going to have a background that's fully opaque, so your overall color will sort of fill the square, and all the proportions will add up to 1. And these are sort of these are where we get these multiplication factors from. This A1 times C1 is multiplying color 1, red, by its opacity, which was 0.5. This A2 times C2 is multiplying the green color, C2, by first the remaining space after taking up 50% of the color for red, and then also by the opacity of the green shade. So it's like 0.5 here and 0.5 here for like 0.25 green. And then this is going to be this times this times this for the background shade, which is going to be 0.5 times like 0.25 times, or some 0.5 times 0.5 times 1. Sorry. Yeah. So that's going to be a remaining proportion of 0.25 for the final background color of blue. And then the sum of these three colors in those proportions is actually equal to what we saw earlier. So this is what you get if you mathematically take the three colors and combine them, and you get one opaque shade that's equal to overlaying these two shades. Does anyone have any questions on that? Cool. That's the end of the workshop. It is now a work session. Thank you guys for listening.